నమస్కారం. డాక్టర్ బిఆర్ అంబేద్కర్ సార్వత్రిక విశ్వవిద్యాలయం విద్యార్థులకు స్వాగతం. ఈ ప్రసారంలో
Hello students, today we are going to discuss about gamma decay. We all know that radioactive materials like uranium, radium, they decay by emitting alpha, beta, gamma radiations. Gamma decay is gamma interaction with matter. When gamma ray photon passes through the matter, it can penetrate to the matter or it can transfer its energy to the matter, or it will transfer part of its energy to the matter and get scattered. The remaining energy will get scattered. Now, we have observed that in the figure it is penetrating to the matter and part of the energy is conveyed to the matter and whole energy is given to the matter. When it is transferring, gamma ray photon is completely transferring its energy, we call it as photoelectric interaction, and when it is a part of the energy is transferred to the matter and most of the incident gamma ray photon is getting scattered. This is called Compton interaction. Another type of interaction also we can observe, that is the pair production of electron and positron. Let us discuss what are the properties of gamma rays. Gamma rays are electromagnetic in nature like radio, infrared, visible, ultraviolet and X-rays. Their energy is highest and frequency is also high, but the wavelength ranges from 10 to the power of -3 angstroms to 1 angstrom. Gamma rays doesn't have any charge, no electric charge, hence they cannot be deflected by electric and magnetic field. Their penetrating power is very high and gamma ray photon has got high penetrating power, and when it interacts with the matter, its intensity decreases exponentially given by the relation I is equal to I0 e to the power of minus mu x. I0 is the incident intensity, x is the thickness of the absorber, mu is the absorption coefficient of the material, and I the intensity of the gamma ray after it traversed through the matter. In our lab, we are determining the linear and mass attenuation coefficient of the materials. Now, let us see how to perform the experiment and what results we get. We will know from our professor Dr.M.Purnanandam sir.
Here we conduct experiment in our lab which determines the linear and mass attenuation coefficient of certain materials called aluminum, copper, lead. So, these are taken in the form of sheets. Now, we see, for example, in this chart, if 100 gamma ray photons are incident on a particular material which is having 1 centimeter thick, you will be able to observe in the chart 90 photons are coming out. The meaning of that is 0.1 is the linear attenuation coefficient. We will find what is also called mass attenuation coefficient in this particular chart. Look to this chart. Here we will send again 100 gamma ray photons are sent into a material having mu is equal to 0.1, 90% are coming out. But if you have another material having a mass attenuation coefficient of 0.033, we require a longer one. You look here, this is 1 centimeter width of this material. This happens to be 3 centimeters width of the material. That means it depends on the density of the material. See, these materials in the equipment that is shown here. These are the 3 different materials. This first line we have got aluminum sheets of different thicknesses. Second line we have got copper material with different thicknesses, and third line we have got lead sheets of different thicknesses. This is a gamma ray source cesium 137, which is being kept in a tray at that particular slot of the holder, and this is a lead sheet arranged in a disc. This is also being kept in another tray. So, gamma rays go from this source through the lead sheet into a thing called GM counter. So, if they are pushed inside, the gamma rays now will go through the lead sheets into the GM counter. The GM counter, which is connected with the help of a cable to the counting system. This counting system will count the counts coming from the source into the system, and such counts are being noted for different thicknesses, and a graph is drawn, and that is shown here in the monitor. Counts per 30 seconds is on y axis, and various thicknesses are taken on the x axis, and the graph comes with 0 thickness. Here the 0 thickness means an empty one that is being put without any lead, the readings are being taken. That is the one. With reference to that, half of the counts available at a particular thickness are taken, and in this case it is found to be 0.11 millimeters. In the case of lead, half of the thickness counts are at 0.11 millimeters. Now, we will see slowly into the another material, call it as copper. The counts, when they become half, the thickness happens to be 0.043, and when it goes to aluminum, the thickness happens to be 0.06 mm. Like this, it will vary from material to material. So, here we will have the values of mu of the mass attenuation coefficient of lead is found to be of the order of 5.55, and copper is being found to be 18.04 centimeter square per gram. For aluminum, because of its low density, we will find the attenuation coefficient happens to be 42.7 centimeters per gram.
We have seen the experiment and we have determined the linear and mass attenuation coefficients of different materials. These results are helpful in identifying the materials which are suitable for operators to save themselves while working with gamma ray equipment for cancer therapy, nuclear power reactors, irradiation of seeds and agricultural produce. Now, what are the factors that are affecting the interaction? The factors that affect when gamma ray interact with matter greatly depends on its intensity of incident energy and nature of absorbing material. Gamma ray photon incident on the matter, and the energy of the gamma ray photon, if it is lost in one interaction with the matter, the resulting effect is called photoelectric effect. In photoelectric effect, the gamma photon transmits all its energy to the electron, and electron will be liberated with certain amount of kinetic energy. and the energy of the photon should be greater than the binding energy of the electron with the nucleus. Then only it is possible to observe the photoelectric effect. The probability of photoelectric effect strongly depends on energy of gamma ray, that is the incident energy of the gamma ray, and atomic number of the atom. When gamma ray loses all its energy in one interaction, the result is photoelectric effect. Probability of photoelectric effect to occur strongly depends on energy of gamma ray, e.g., and atomic number Z. Now, the transfer of energy takes in different mechanisms. Let us observe what is happening. The gamma ray photon transfers all its energy to the most suitable electron located in one of the atomic shells and is removed from the atom as photoelectron. The gamma ray photon transfers all its energy to the most suitable electron located in one of the atomic shells and is removed from the atom as photoelectron, and the photoelectron will have kinetic energy. The remaining energy is deposited near the interaction site. The gamma ray photon ceases to exist after the interaction. Let us see what are the conditions that are to be satisfied in order to get the photoelectric effect. Photoelectric interactions are most probable when the electron binding energy is slightly less than the gamma ray photon energy. It means the gamma ray energy should be greater than the binding energy of the electron. If binding energy of the electron is greater than energy of the gamma ray photon, photoelectric interactions are most probable when the electron binding energy is slightly less than the gamma ray photon energy. If binding energy of the electron is greater than the energy of the gamma ray photon, the interaction does not occur. Up till now, we have seen how photoelectric effect occurs. Now, in the photoelectric effect, the complete energy of the gamma ray photon is transferred to the atom. In the case of Compton effect, the energy of the photon is such that it will knock out the weakly bound or free electron from the atom. If a gamma ray is incident on a material with free or weakly bound electron and transfer part of its energy to the electron which goes away from the material, the remaining energy is scattered. Here the photon is interacting with the weakly bound electron and a part of the energy is transferred to the electron and the electron is going like this and the remaining part of the energy is scattered as scattered photon. The energy of the ejected electron will be equal to energy of the incident photon and energy of the scattered photon. Now, the photon is interacting with the weakly bound electron and the electron is liberated and it is moving in this direction and the scattered photon is moving in this direction. So, the scattered photon is making an angle with the incident direction. Let us suppose the angle made by the incident and scattered gamma ray is theta, then the energy of the scattered photon is given by E scattered is equal to m0 c square divided by 1 minus cos theta plus m0 c square by E, where theta is the angle between incident and scattered gamma ray and m0 c square is the rest energy of the electron. Now, if we observe this figure, the gamma ray photons are emitted from the tube and they are falling on the carbon scatterer. Now, if the angle of scattering is 0, we observe no scattered peak or no scattered ray. If the angle between the incident and the scattered ray is 45 degrees, then we are observing the incident gamma ray peak and scattered gamma ray peak. Now, there is a difference between the wavelength of the two peaks, and this is called Compton shift, and it is of the order of 0.007 angstroms when the gamma ray photon is scattered at an angle of 45 degrees. When the gamma ray photon is scattered at 90 degrees, if we observe this figure, we can see that the incident peak and the scattered peak are separated by a large distance, and the Compton shift is given by 0.024 angstroms. When we observe the scattered ray at an angle of 135 degrees, we can see that the peaks are displaced with a shift of 0.041 angstroms. So, the angle of scattering changes as the angle of incidence. Now, the Compton shift we can relate with theta by the relation d lambda is equal to lambda dash minus lambda, which is equal to h into 1 minus cos theta divided by m0 c. Wavelength, frequency and energy of scattered gamma rays depends on theta. If theta is equal to 0, the scattered gamma ray has maximum energy. If theta is equal to 0, the scattered gamma ray has maximum energy. If theta is 180 degrees, it has minimum energy and the recoil energy of the electron is maximum. Now, the energy of the scattered ray is equal to energy of the incident ray, then we get a coherent Compton scattering. We observe coherent Compton scattering when energy of the incident ray is equal to the energy of the scattered ray. The individual amplitudes of each of the atomic electrons are added, whereas if the energy of the incident ray is greater than energy of the scattered gamma ray, it is called as coherent Compton scattering, and the individual intensities of the atomic electrons are added. In the case of coherent Compton scattering, the individual amplitudes are added, whereas in the case of incoherent Compton scattering, individual intensities of the atomic electrons are added. Now, the probability of Compton scattering is less strongly dependent on incident energy and the atomic number compared to photoelectric effect. In photoelectric effect, it depends upon the incident gamma energy and the atomic number, whereas in the case of Compton scattering, the probability of Compton scattering is less strongly dependent on E incident or Z compared to photoelectric effect. The total Compton cross section decreases with energy of incident gamma ray. While designing effective shielding for high energy gamma rays, the angular variation has to be taken care of.
Problem of pair production is having its root in the inability of Schrodinger wave equation to explain the relativistic invariance or relativistic effect of the electron that is moving, particularly when it is a free electron. Hence, another scientist called Dirac, he tried to explain this particular thing with the help of an equation called E is equal to, this E is the energy of the eigenvalues for free electron, E is equal to plus or minus p square plus c square plus m0 square c to the power of 4 whole under root. This particular equation has got both plus or minus. When energy is plus, it is being understood by the scientists all over very conveniently. When the energy is minus, it is one of the very difficult things to understand. But he proposed that if it is a plus, it is an electron. If it is a minus, minus energy is attributed to another particle called a positive electron. Hence, he proposed a positron particle in his theory. So, later it has been observed that if sufficient amount of energy is given to the large Z material, we will have a energy incident gamma ray energy must be utilized in making the a pair of particles having their kinetic energies Ke plus and Ke minus, kinetic energy of the positron, kinetic energy of the electron, and consequently this must be added to the difference in the energy of both these particles, that is twice the m0 c square rest mass of these particles. Hence, we will have what is called pair production. So, in the pair production, the disappearance of the electron from a negative energy state leaves what is called a hole. Hole is a place where there is no electron, but consequently they called it as a positron and maintained the concept of hole in semiconductors also, which means the appearance of a positron. The appearance of an electron in a positive energy state means the appearance of an ordinary electron. Hence, a pair is created in the electric field in the neighborhood of the nucleus of high Z, high atomic number, to maintain the conservation of energy and momentum. So, in this chart you will observe this is the energy axis, y axis, and you will have all these are bands of energy. These are called negative bands of the energy, whereas our positive electron called positron or hole is available in the negative band of the energy, whereas our regular electron called negative electron is available in the positive of that. This positive electron or hole is available at the negative energy state. The difference between these two happens to be 2 times m0 c square. So, our equation says that this is amount of energy supplied must be 2 times m0 c square plus the kinetic energy of the positive electron and the kinetic energy of the negative electron. Like this, a pair of particles called electron positron pair, they are formed. Their interaction with matter will be like this. When gamma ray enters into the matter, it tries to ionize and produce a pair of particles, positive called positron, negative called electron, and these two are created when they are brought nearer with suitable amount of energy. Then they will collide and annihilate and they produce the energy equivalent of electron and energy equivalent of positron. So, hence the energy released is also shown here. That means, annihilation of matter, creation of matter, both are being observed in the pair production. So, these two give us the idea that a mass is created by the energy and a energy is also created by the mass. So, the Einstein's concept of E is equal to mc square, the energy mass relation, is thoroughly explained, fully satisfied in the production of the pair of the particles and also annihilation of the pair of the particles.
పాఠ్యాంశాలపై మీ సూచనలు, సలహాలు, సందేహాలు మాకు తెలియచేయండి. మీ సూచనలు, సలహాలు, సందేహాలు మాకు తెలియజేయవలసిన చిరునామా: డైరెక్టర్, ఆడియో విజువల్ ప్రొడక్షన్ అండ్ రీసెర్చ్ సెంటర్, డాక్టర్ బిఆర్ అంబేద్కర్ ఓపెన్ యూనివర్సిటీ, ప్రొఫెసర్ జి రామరెడ్డి మార్గ్, రోడ్ నంబర్ 46, జూబ్లీ హిల్స్, హైదరాబాద్ 500033.